I have this really distinct memory from high school physics. We were watching that famous Carl Sagan clip, you know the one where he talks about the pale blue dot.
Oh, yeah. A mote of dust suspended in a sunbeam. It is a beautiful image.
It is. It really is. But the takeaway I got back then was this overwhelming sense of, well, mediocrity. Like the lesson was basically don't get a big head. You live on an average rock orbiting a boring average star in the forgotten suburbs of a run-of-the-mill galaxy.
Right. That's the Copernican Principle,
Oh.
or as we usually call it in the field, the Mediocrity Principle.
Yeah, the mediocrity principle, which is honestly a bit of a buzzkill. It paints this picture that the universe is just teeming with life because, hey, if we happen to evolve here by accident in such a boring average place, we must be happening everywhere.
Exactly. Just add water.
Right. The soup mix theory of life.
The soup mix theory.
Yeah.
Yeah, the excitement has always been that if you have the basic ingredients, energy, water, organics, the cake inevitably rises. Like if the universe is vast enough, life just has to be everywhere.
But, and this is why we're doing this deep dive today, we are looking at a stack of research that essentially takes that mediocrity principle, crumbles it up, and throws it right in the trash.
It really does.
We're digging into the work of astronomers Guillermo Gonzalez and Jay Richards, and also looking at the rare Earth hypothesis from geologists Peter Ward and Donald Brownlee. And I want to set the mission for today's deep dive right off the bat for you listening. We are exploring the idea that Earth isn't just lucky.
No, not just lucky. These sources aren't saying, oh, we got a good roll of the dice. They're arguing that the hard data from astronomy and geology suggests we are the winners of a cosmic lottery that is so insanely specific that luck it stops being a mathematically viable explanation.
They are saying Earth is not mediocre at all.
They're saying Earth is a complete freak of nature. And more than that, and this is the part that actually blew my mind reading through the notes, they argue that the very specific conditions that keep us alive are the exact same conditions that allow us to do science.
That the universe is designed for discovery, which is a huge claim.
Massive claim.
So let's strip this down. Let's start with the basics. If we aren't the average tenants of the universe, where do we actually live? Let's talk cosmic real estate.
Let's start with the neighborhood, because you mentioned that romantic idea of contacting the aliens, right?
Yeah.
Back in the 70s, Frank Drake and Carl Sagan sent that really famous radio message out toward M13.
The Great Cluster in Hercules, I remember this. It's this massive ball of 250,000 stars. And if you're just playing the numbers game, that feels like the jackpot. You aim for the biggest crowd of stars, right?
That was the intuition, yeah. But Gonzalez points out in the source material that doing that was actually a complete waste of energy.
A waste of energy. Why? I mean, you have 300,000 suns in one spot. Surely one of them has a planet with a radio.
It's actually extremely unlikely, because M13 is a globular cluster. Think of it as a retirement home for stars.
Okay.
They are incredibly ancient. They formed when the universe was essentially just hydrogen and helium. They lack what astronomers call metals.
Oh, wait, let's clarify that for everyone. Because in astronomy, metal doesn't just mean like iron bars or aluminum foil, right?
Right. Yeah, to an astronomer, basically anything heavier than helium is a metal. Carbon, silicon, iron, the literal stuff you need to build a rock. You cannot build an Earth out of gas. And because those clusters are so old, they just haven't had enough generations of stars dying and exploding to create those heavy elements.
So it's a ghost town. There's no solid ground to stand on.
Exactly. And even if you did somehow have a rocky planet there, the stars are packed so tightly together, sometimes light years apart or even less, that the gravity in there would be total chaos.
So your orbit gets messed up.
You wouldn't have a stable orbit at all. Your planet would be ripped apart or just violently flung into deep space.
Okay, so dense clusters are out. But what about the spiral arms? When you see a picture of the Milky Way, the spiral arms are the iconic part. That's where all the bright lights are.
The problem is there's too much action there. The spiral arms are kind of like the inner city during a riot. It's where active star formation is happening. And that means you have massive stars burning really hot, dying young, and going supernova.
And I'm going to go out on a limb and assume having a supernova go off next door is bad for property values.
It is a complete sterilization event. If a star explodes within, say, 30 light years of you, the radiation can strip your planet's ozone layer entirely.
Wow.
And then on top of that, you have giant molecular clouds. These are massive nebulas that act like gravitational bulldozers. If your solar system passes through one of those, it disrupts the orbits of all your planets and comets.
So you can't be in the cluster, you can't be in the arms, and I'm guessing the very center of the galaxy is even worse.
The center is a war zone. You've
Yeah.
got the supermassive black hole, intense radiation, an incredibly high density of exploding stars. It's a mess. But, and here's the kicker, you also can't go too far out to the edge.
To the boonies.
Right, the galactic outer rim. Out there, the star formation was too slow, there just aren't enough heavy metals. So you can't build a planet large enough to hold onto an atmosphere.
So this is the first big filter they talk about, the galactic habitable zone.
Yes. It is a surprisingly narrow ring. Earth is tucked safely right between the Sagittarius and Perseus arms. We have enough heavy metals to build a solid rocky Earth, but we're in a quiet enough suburb that we aren't getting fried by supernovae every few million years.
We're in the Goldilocks ring of the galaxy itself.
Exactly.
But let's zoom in a bit, because even if the galactic neighborhood is good, the textbooks always tell us that our specific house, the sun, is nothing special. They always call it a common yellow dwarf, which just sounds so underwhelming.
It really does. But that is one of those textbook facts that is actually quite misleading. Gonzalez notes in the research that the sun is actually in the top 10% of the most massive stars in the entire galaxy.
Wait, top 10%? I totally thought the vast majority of stars were just like ours.
Not at all. If you picked a star perfectly at random in the Milky Way, you wouldn't get a sun. You would get a red dwarf. They make up about 80% of the stellar population.
Okay, so let's play devil's advocate here. Why can't I be, a Kryptonian living under a red sun? What is the deal breaker for life there?
There are three big deal breakers. The first is just the heat. Red dwarfs are much, much cooler than our sun. So to get enough warmth to have liquid water, your planet would have to orbit extremely close to the star, like Mercury close.
And that messes with the gravity, right?
Significantly. When you are that close to a star, you get tidally locked. The star's gravity literally grabs the planet's rotation. So one side faces the star forever, and the other side faces away forever.
So one side is a permanent roasting oven, and the other is a frozen wasteland in perpetual night.
Exactly. It is very hard to circulate an atmosphere that keeps life alive in those extremes. But even if you somehow could, red dwarfs are incredibly temperamental. They are what we call flare stars. They have these magnetic tantrums where they can double in brightness in minutes.
So you're sitting there in the twilight zone of this planet, maybe trying to farm some space potatoes, and suddenly the star just screams at you with X-rays.
Yep. And since you're orbiting so close, that flare completely strips away your atmosphere. But the subtlest problem with red dwarfs is actually the light spectrum itself. They don't put out much blue light.
Why does the color of the light matter?
It comes down to photosynthesis. Plants on Earth rely on a very specific balance of red and blue light to be efficient. But more importantly, blue light is high energy. It's what helped create the oxygen-rich atmosphere we have today. A red sun might just mean a low-energy, low-oxygen world.
So our boring yellow sun is actually a highly specialized, high-performance engine. It's incredibly stable. I think the notes said its luminosity varies by only 0.1%, and it emits the perfect light for high-energy food chains.
Right. But the sun isn't working alone to keep us safe. We have to talk about the bouncer at the club, Jupiter.
I love this concept, the idea that a gas giant isn't just decoration out there in the dark.
It's essentially a vacuum cleaner. Jupiter is 300 times the mass of Earth. Its gravity is so immense that it acts as a literal shield. It attracts or deflects comets and asteroids that usually come zooming in from the outer solar system.
The sources mentioned the Shoemaker-Levy 9 impact. I remember seeing photos of that.
Yeah, back in the 90s. We watched a comet break apart and slam into Jupiter with the force of millions of nuclear bombs. If Jupiter wasn't there, or Saturn wasn't helping out, those debris fields would pass right through the inner solar system. Earth would be getting constantly pummeled.
We'd be resetting evolution every few million years.
We simply wouldn't have the time to develop complex intelligence. We'd be stuck at the bacteria stage because the surface would constantly be melting from impacts.
Wow. And there's another detail about the solar system that I found really surprising in the notes. The shape of the orbits. Apparently circles aren't the norm.
This was a massive shock to astronomers. When we first started finding exoplanets, we expected nice, orderly, circular orbits like ours, because that's all we knew. Instead, we found absolute chaos. Gas giants swinging in wildly elliptical orbits, zooming super close to their star, then way, way out.
And if Jupiter did that?
Disaster. If Jupiter had an elliptical orbit, its gravity would yank on Earth. It would pull us right out of our circular path. We'd spend 3 months freezing out near Mars and 3 months broiling near Venus. A circular orbit is crucial for a stable climate, and we're incredibly lucky that our giant neighbors behave themselves and stay in their circular lanes.
Okay, so we have the right galaxy zip code, the right star, a big brother bodyguard in Jupiter. Let's land the ship and look at Earth itself. The Rare Earth book makes a huge deal out of our moon, which, again, feels like something we completely take for granted.
We absolutely do. Our moon is freakishly large compared to the planet it orbits. No other rocky planet in the solar system has a setup anything like this. And it's not just up there for romance or tides. It's an anchor.
An anchor for the tilt, right?
Right. Ideally, you want a planet to stay tilted at a steady angle. Earth is at about 23.5 degrees. That gives us mild, predictable seasons. Without the moon's gravity stabilizing us, calculations show Earth's axis could swing wildly, like from 0 to 85 degrees over time.
85 degrees is basically lying completely on your side.
It means the North Pole points directly at the sun. You'd have half the planet in total daylight for months, literally cooking, while the other half is in a deep freeze, and then it flips. The climate chaos would be totally impossible for complex animals to adapt to.
So the moon keeps the seasons predictable. Now, I want to ask about the ground beneath our feet, plate tectonics. I usually think of earthquakes as a bug in the Earth system, something that breaks things and kills us, but the sources call it a vital feature.
A critical feature. In fact, Ward and Brownlee argue that without plate tectonics, you simply do not get animal life. Period.
Why? That seems like a huge leap.
It comes down to two reasons. First, it's the planet's thermostat. Rain naturally scrubs carbon dioxide out of the air. That carbon gets locked into rocks on the surface. If that was a one-way street, we'd eventually run out of CO2, the greenhouse effect would collapse entirely, and Earth would freeze.
A snowball Earth.
Right. But plate tectonics drag those carbon-heavy rocks down into the mantle, melt them, and then volcanoes spit that CO2 back out into the sky. It actively recycles the atmosphere to keep us warm. But the second reason is what they call the water world problem.
Now, when I hear water world, I assume that's a good thing. Water equals life, right?
You definitely need water. But if the Earth were even slightly larger, or if we didn't have plate tectonics constantly buckling the crust to create mountains and continents, gravity would smooth the surface out. And the water we have would cover the entire globe to a depth of 2 or 3 kilometers.
Okay, so we'd all just be dolphins.
Yeah.
What's the scientific issue with a global ocean?
The issue is the food chain. In a deep global ocean, the life-essential minerals, things like phosphorus and iron, just sink to the bottom. They get buried in the dark abyss. On Earth, we have land. So rain washes nutrients off the rocks, down the rivers, and into the shallow coastal waters. That is where the massive explosion of life happens.
So in a water world, the surface of the ocean is actually a desert.
A complete biological desert. You might have some simple algae drifting around, but you would never have the energy density required to support complex, large creatures like us.
And the sources mentioned salt levels too, didn't they?
Yeah, that's a big one. Without land masses to trap salt in shallow tidal pools, which we call evaporates, the oceans would eventually become supersaturated. This all builds up over billions of years. It would get so briny that basic cellular chemistry would just stop functioning.
It is so fascinating. We tend to think Earth-like just means it has water and isn't actively on fire. But the rare Earth hypothesis is saying you need this insanely specific cocktail. You need the specific galaxy zone, a stable yellow star, a Jupiter shield, a massive moon, and an actively moving geology.
Which brings us to a really important distinction Ward and Brownlee make. They actually think simple, lifelike slime molds bacteria might be fairly common in the universe. The soup mix theory works fine for bacteria. They're tough. But complex life, a technological civilization, that requires pulling the winning lottery ticket on every single one of those factors.
So that covers the habitability side of the argument. We are safe, we are warm, and we are stable. But this deep dive has a second half. And this is the part from Gonzalez and Richards that feels, honestly, it feels almost eerie.
The correlation.
Right. They argue that the conditions that make us safe are the exact same conditions that allow us to see. That habitability correlates directly with measurability.
It's a remarkably bold hypothesis. It essentially suggests the universe isn't just uniquely set up for life. It is set up to be understood by that life.
And the best example they give of this is the solar eclipse.
It is arguably the most striking coincidence in the entire solar system. Just think about the geometry for a second. The sun is 400 times larger than the moon. giant ball of nuclear fire, relatively small rock. But the sun is also exactly 400 times further away from Earth than the moon is,
So when we look up in the sky, they look exactly the same size.
down to a tiny fraction of a percent. And because of that completely perfect fit, when the moon passes in front of the sun, it perfectly blocks the blinding bright disk, the photosphere, but it leaves the sun's atmosphere, the pink chromosphere and the white corona, perfectly visible.
And Gonzalez makes the point in the book that this isn't just a pretty light show for tourists. This is a scientific instrument.
A genuinely crucial one. Because we could block the sun's glare so perfectly, we were able to discover helium. It was actually found by looking at the sun's atmosphere first. It allowed us to learn how to analyze stellar composition. And famously, in 1919, a total solar eclipse allowed astronomers to verify Einstein's theory of general relativity.
By seeing the background starlight bend around the darkened sun.
Exactly. Which you can only see if the fit is perfect. If the moon were slightly bigger, it would block that bending starlight entirely. If it were slightly smaller, the sun's glare would completely blind you. We're literally in the one place in the solar system where observers exist, and it just happens to be the one place with the best possible view of stellar physics.
It goes way beyond eclipses, though. It's also about the literal air we breathe. We need an oxygen-nitrogen atmosphere to support our high-energy metabolisms.
Right. But it just so happens that an oxygen and nitrogen mix creates a uniquely transparent atmosphere. If we lived on a planet with a methane-rich haze, or a thick cloudy soup like Saturn's moon Titan, we could perhaps survive if our biology adapted, but we wouldn't be able to see the stars.
We'd be flying blind, no astronomy, no cosmology.
We wouldn't even know the rest of the universe existed beyond our own cloud layer.
Yeah.
And you can scale that up. Go back to our location in the galaxy. We are out in the suburbs.
Away from the bright lights of the inner city.
Exactly. If we were in a dense star cluster or the galactic center, the night sky would be absolutely blazing with local starlight. It would be gorgeous, but we would be completely blinded by our own neighborhood. Because we are in the boring, dark suburbs, we can actually look out past our galaxy into deep space. We can measure the cosmic background radiation.
Which is what gave us the definitive proof of the Big Bang.
That is the core argument. If we were anywhere else, even if we could somehow survive the radiation in the supernovas, we wouldn't be able to observe the distant universe. We wouldn't be able to discover the history of the cosmos.
That is the true aha moment for me. We aren't just surviving here in a bunker. We have a front row seat to the cosmos. It's almost like we're in an observatory that also just happens to be a life support garden.
And that brings us to the trilemma that the source is present at the end. When you look at all these factors stacked on top of each other, you really only have three options to explain it all.
Okay, option one is law. Just the sheer laws of physics.
The idea that the physics of the universe inevitably produces life. But as we've seen, the simple soup mix theory is really struggling against the hard data. The required conditions are just far too specific. You can't just invoke physics to explain why the moon is exactly the right size to perfectly block the sun and also keep our seasons stable. Physics doesn't demand that.
Right. Which leads to option two, chance. We are just the absolute luckiest fluke in the history of existence.
And, to be fair, that is a scientifically valid position. It's often tied to the multiverse argument. If there are infinite universes, one of them has to be perfect, and we just happen to be in it. But as you stack up the coincidences, the moon, the Jupiter shield, the plate tectonics, the eclipse geometry, the galactic habitable zone, the odds get infinitesimally small. You start needing a massive amount of luck to make the math work.
Which leaves option three, design.
Purpose. The sources, particularly Gonzalez and Richards, argue that the measurability factor, the fact that we can do science, tips the scale. The fact that the universe seems accessible to our minds, that we are placed in the one perfect spot to decode it, suggests to them that our discovery of the universe isn't an accident.
There is a quote from the astronomer John O'Keefe in the notes that I think lands this perfectly. He says, "We are, by astronomical standards, a pampered, cosseted, cherished group of creatures."
It completely flips the script on that lonely speck feeling we started the deep dive with. Instead feeling incredibly small because the universe is so vastly big, you realize the universe might be vastly big. Precisely so that we have something grand to explore.
That while we are physically tiny, our role as observers might actually be centrally significant to the whole thing.
Exactly. If we are the only ones with a clear view, maybe our job is to do the looking.
It definitely changes the way I'm going to look up at the night sky tonight. Not just as this cold, indifferent void, but maybe as something waiting to be seen. which is a thought I want to leave you with as you go about the rest of your day. Next time you look up, ask yourself if you're just an accident of chemistry or if the cosmos is a puzzle designed specifically for you to solve.
It's a profound shift in perspective.
That's it for this deep dive into the privileged planet. Thanks for listening and keep wondering.